So hi guys, welcome to AOSP customization. So from some last videos, I was trying to explain AOSP with some AI videos. Some people liked it, some did not like. So I thought let's create one AOSP customization full playlist end to end on this channel. In this playlist, we will go through each and every AOSP project practically. I will do all practicals on my Ubuntu system with easy explanation. So my name is Samir. I am working as an AOSP platform engineer for over some past few years. I have spent lot of time working with AOSP custom ROMs, debugging platform issues, customizing framework changes and all. So who can see this series? So if you are an Android developer and want to move to AOSP, or if you are preparing for interviews, or if you are an embedded Android developer, or any person curious about Android internals can watch this series. We will start this from very basic fundamentals to the expert level customizations. So in this first video, we are going to start with a complete roadmap of AOSP. So let me walk you to the roadmap. So here this is the AOSP Insider side and you can go to this roadmap. As you can see here, this roadmap is there. So we have designed this roadmap. You can come to AOSP Insider, log in and track your progress here. Whenever you complete some topic, you can mark completed here or remove also. So the first thing is language and tooling basics. So see, to start with AOSP, you will need basics of Java and Kotlin because Android framework is primarily written in Java, while modern applications are commonly developed in Kotlin. As you explore AOSP source code, you will spend a lot of time reading Java classes, understanding object-oriented programming concepts, and like how that methods are calling each other, that things. Then you should know the basics of C and C++. So as we move to the hardware, you will encounter like a native code written in C and C++. Native code, some native libraries are there, and Linux kernel level drivers are there. Most of the things are written in C and C++. You will also need to have a basic understanding of Git and Gerrit. So AOSP is made up of 100 of Git repositories. These are working together, so the understanding Git commits, how branches are working, how you can raise the Gerrit for open source AOSP, these things so in future you may do these things. In also C section you can see Ubuntu, Debian basics and basics of Android. So this full series we are going to do all the practicals in Ubuntu system, and of course you also need the basics understanding of Android also. Okay, so as we move to the next section, you will see AOSP foundations. This is where our real AOSP journey begins. So before writing a single line of framework code, we first need to understand what AOSP actually is, and how it's organized, and how Android is built from millions of lines of source code. In single line, if I say the AOSP is Android open source project, it's the open source operating system maintained by Google. AOSP contains the framework, system applications, native services, build systems, Android specific Linux kernel, and almost everything required to build an Android operating system. So what actually people don't know is that AOSP is not the same as Android that comes most of the phone like Samsung, Xiaomi, OnePlus, Motorola, Pixel and many others. So actually all started building with AOSP, but each company adds its own customizations and applications and hardware support. In future we will explore in source code where the AOSP ends and where OEM means like Samsung customizations begins. Now this AOSP versus Android GMS. So now you may have heard the terms like GMS or Google Mobile Services. That is like an extra layer added on top of AOSP. It includes things like Play Store, Google Play Services, Gmail, Google Maps, YouTube and many other Google applications that most of us use every day. While working on AOSP, whenever we will build, it will look like running some commands, but behind the scenes multiple build tools works together. Blueprint files describe modules, Zoom processes those definitions, Ninja will perform the actual compilation, and there is some helper commands which will simplify the workflow for us. These things whenever we will do practically, you will understand better. We will open these files, understand what each tool does, and we will create our own modules from scratch. Before we dive deep into individual components, we need to see the complete picture of AOSP. This is not like an application is running on Linux. It's layered architecture. At the bottom it is the Linux kernel. Above that, the hardware abstraction layer. Then native libraries, Android Runtime, then the Java framework is there, and finally the applications we use every day. Once you understand how these layers communicate with each other, every future topic becomes much easier to follow. Then there is a partition layout. On physical device, the Android is not stored as a giant folder, we can say. It's divided into multiple partitions. For example, system partitions, vendor partitions, product partitions, boot, recovery, super, user data. These all are partition which, like, each partition is having specific responsibilities. Understanding this layout is essential whenever we are building Android for flashing devices, debugging boot issues, or implementing OTA updates. We will also see the dynamic partition components like AB slot, seamless OTA update in detail in this series. At this point, you should have a clear picture of what AOSP is, where the source code comes from, how Android is built, how the operating system is structured, and how it is organized on device. Now the next layer is application layer. Whenever you unlock your phone and open an app like WhatsApp, YouTube, or settings, you are interacting with this application layer only. So one thing many developers don't realize, that not all Android apps are the same. Some are regular user installed apps, some are system apps, and some are privileged apps that have access to permissions normal applications can never request. Understanding these differences is essential for if you want to customize Android or work with AOSP. Every Android application is built using a few fundamental things like activities, services, broadcast receivers, content providers, and intents. That all we will explore in detail. We will also explore where the application actually live inside Android. Some are stored in the system partitions, some are in vendor partitions, some stays in product partitions, or the user data partition. This location can affect how the app is updated, what permission it can have, and many other things. In the dedicated videos of this module, we will build applications and trace their life cycle, understand how intent works, and how Android launches the activity, launches the app when you are tapping the icon of that application, and we will see how these applications are communicating with Android framework. So the next is Android framework and system services. So after understanding applications, you should be able to understand that who is launching these applications, who is installing, or who is deciding which app can access the camera or the microphone. So that all is being done from the framework layer. You can think of the Android framework as the brain of the operating system, because like applications don't talk directly to the hardware, instead they communicate with the framework, and the framework takes care of everything behind the scenes. It will provide the APIs that every Android application will use. Inside the framework there are many system services, and each one has a specific responsibilities. For example, activity manager service manages application lifecycle. Package manager service is responsible for installing applications and managing packages. Window manager service controls the window and what appears on your screen. These are just a few examples. Android contains dozens of services working together and run the entire operating system. Now the binder. So there is an interesting question, like if an application and system services are running in different processes, how they talk to each other. That's where binder comes in. Binder is Android's IPC mechanism, or inter-process communication mechanism, we can say. It allows different processes to communicate efficiently and securely. Along with binder, we will also see AIDL, which makes defining these interfaces much easier. We will explore the Android framework source code, understand how these services are created during boot, trace the real API calls from an application to the framework, and even we will build our own custom system services also. So now we are having basic understanding of Android application and framework layer. We will next cover the resources, so that you will know whenever you will switch your phone from light mode to dark mode, or change the system language. How does Android know which resource to use? That's what Android resource system will handle. Android keeps almost all the user interface separate from the actual code. All the layout, string, icon, colors, and animations are stored as resources. Because of this, applications are easier to maintain, translate into different languages, and adapt to different screen sizes or different devices and different themes. While going through this module, we will see how Android compiles resources and how they packaged into system, how resource IDs are generated, and how Android resolves the correct resources at runtime, and how you can customize the look and feel of Android using overlays. So when you understand resource system, you will realize that many Android customizations don't require changing Java code at all. They can often be achieved simply by replacing or overriding some resources. So far, we have explored Android applications, the framework, system services, and the resource system. Now the next is Android runtime. There is an interesting question. When you start some applications, what actually executes that Java or Kotlin code? And what happens when Android needs to perform something that's too close to the hardware or requires maximum performance? That's where Android runtime and Java native layers will come in picture. In this module, we will understand how applications actually run, what happens behind the scenes when you launch some applications, and how ART helps Android to deliver both performance and efficiency. The next is native layer. So not all in Android is written in Java or Kotlin. Many core Android components are implemented in C and C++ because they need direct access to the operating system on demand, or demand the highest possible performance. Components like libbinder, libc, and graphics library, there are many system demands all lives in native layer. We will also learn how Java code communicates with native code, C and C++ using JNI, and when developers use the NDK to build native applications and libraries. So up to this point, we have looked at the Android as a collection of different components. Before looking at Android lower layers, it's better to know how Android boots when you press the power button. So in AOSP, Android full booting process is a carefully designed sequence where every component is having a specific role. So here the first is boot ROM, which will start the bootloader, and bootloader will do some of its tasks, and it will at the end start the Linux kernel. Linux kernel, like where all the drivers and binder and many critical things stays, which will eventually starts the init process, which will brings up essential system services, and at the end init will start the zygote, which will prepare the runtime environment. Then the system server starts, the core services, then the core services, and finally the launcher appears on the screen, ready for you to interact with your device. By the time we reach this module, you will already know what each component does individually. Now we will connect them together and understand the complete startup sequence from the beginning to end. Instead of seeing them as a separate topics, you will see how they depend on each other to bring Android to life. We will trace the entire boot flow step by step from the moment the device powers on until the home screen appears. And we will explore each stage in actual AOSP source code also, to understand the who starts whom, and why the startup order matters, and how to debug boot problems when something goes wrong. So the next thing we will see is process and memory management. This is one of the most important thing to learn in AOSP or any operating system in the world, because of this only we can run all apps simultaneously, process tastes and priorities. So like Android doesn't treat every process the same. The app you are actively using gets the highest priority, while apps sitting in the background are managed differently. Android is consistently deciding which process should stay alive, which can be paused, and which can be safely removed when the system needs resources. Now for the memory management, memory is one of the most valuable resources on the device. Android has to balance speed, responsiveness, and stability, all while multiple applications are competing for memory. We will explore how Android manages RAM, what happens when memory becomes limited, and how the system decides which process to terminate first instead of simply crashing the device. The power management Like for example, battery life is another area where Android does a lot more than you think. The system continuously monitors what applications are doing in the background and limits unnecessary work to save the power. Features like wake locks, doze mode, app standby, and thermal management and all works together to make sure your phone stays responsive without draining the battery. So in this module we will understand how Android prioritize processes, how manages memory under pressure, and how it controls background executions and optimize the battery life. So from now here things get more interesting. So far we have explored everything happening inside the Android operating system. But at the end of the day, Android has to interact with the real hardware. When you take a photo or play music or turn on the torch, for this Android will use the HAL. So the HAL is hardware abstraction layer and it acts as a bridge between the Android framework and Linux kernel. It exposes standard hardware interfaces so the framework can access hardware without interacting directly with the device drivers. Below the HAL in Android architecture, there comes the Linux kernel. This is the lowest layer of Android operating system. The kernel is responsible for communicating directly with the hardware. Kernel manages device drivers, memory, scheduling, security, and many of the core services that Android depends on. Without the kernel, Android would not be able to interact with the physical device at all. Modern Android also separates the Android framework from vendor specific implementations. This separation makes Android updates much easier because the framework and vendor code can evolve more independently. So we will see the things like Project Treble, WinTF and VNDK and understand how they help to maintain compatibility between Android and hardware specific components in future dedicated videos. So the next is hardware subsystems. So till now we have seen how Android reaches the hardware. Now there are some subsystems you should be knowing. Every time you are doing any task on Android, for example listening to music, taking a photo or using a Wi-Fi, then a dedicated hardware subsystems make your phone feel faster and responsive. So first let's see the graphic stack. So every animations, app window, transitions and every frame you see on your screen goes through the Android graphic stack. For checking this in detail, we will explore surface finger, buffer queue, and hardware composer. These things. Then the next is audio architecture, audio subsystem. If you are playing a music or making a phone call or recording your voice, for these kind of things, Android has to route the audio to the correct hardware. We will explore how audio flinger, audio policy manager and the audio HAL works together to deliver smooth experience. Then the camera, one of the most complex part of Android. So capturing a single photo involves multiple layers working together. From the camera application to the camera framework, then camera service, then camera HAL and finally the image sensor. We will trace the complete journey and understand what happens every time whenever you are pressing the shutter button. Then for input, like every tap, swipe, button press and gesture will start as a hardware event. Android will receive those events and processes them and delivers them to the correct application in just a few milliseconds. We'll follow this path through components like event hub, input reader and input dispatcher. Then for connectivity, in Android is handled by connectivity subsystems, so the modern smartphones are constantly communicating with the world around them, whether it's Wi-Fi, Bluetooth, NFC or the cellular network. Android provides dedicated components to manage each of these technologies. We will understand that how these connectivity stacks are designed and how applications interact with them through the Android framework. Finally, the display system. So we will understand how it controls the display panel, adjusts brightness, manages different refresh rates, and how it works with modern display technologies to deliver a smooth visual experience like VRR and all. So basically for AOSP developers, it's very crucial to become master of at least one hardware subsystem. We will take each hardware subsystem one by one and explore its complete architecture from the Android framework to the HAL and all the way down to the hardware. So after understanding AOSP fully, there is no point if you are not able to fix a small bug. So in real world, things don't always works as expected. You should be able to debug and fix the issues like app crash, services failing to start, or device stuck in the boot loop, or some performance issue. So every AOSP developer or engineer spends a lot of time in debugging. The good news is Android provides powerful tools to help us understand what's happening inside the system. We should learn how to read logcat, use ADB, analyze bug reports, inspect DUMSys outputs, and investigate ANRs, and understand native crashes through the tombstone logs. The terminologies which you are not able to understand for now, don't worry, we will go through in detail in this series. So by the time you will got to know all the things. Now for the security is built into every layer of the AOSP. For example, applications runs inside their own sandbox, and permissions are carefully enforced, and the operating system is designed to prevent unauthorized access to system resources. That's where SELinux comes in. Then the Android permission model and Android verified boot and so this is how Android protects both user and operating system from potential security risks. So if full AOSP build you are able to make with your changes, I mean your own custom ROM, then the next question is how do we know that it's ready for the users? So that's where Android testing and compliance tools comes in. We will learn about test suites like CTS and VTS and understand why they are important, and see how in the real world companies are using them to verify that Android behaves correctly and remains compatible across devices. So then for making AOSP interesting, you can customize your own AOSP and make your own custom ROM. So we can customize the user interface and add our own features, modify system UI. We will create our own launcher, and we can create custom themes and some hardware specific functionalities also we can add to our custom ROM. We will learn how these customizations are done, where those changes live in the source tree, and how to modify Android while keeping the system stable and maintainable. So the next is OTA updates and releases. Only building Android is not enough for production. So device will need the security updates, bug fixes, feature updates, and major Android upgrades like Android 15 to 16 or 16 to 17 in future. We will explore how Android update works, how OTA packages are generated, and what is AB seamless OTA, how AB seamless OTA updates reduce downtime, and how devices rarely safely transition from one software to another. We will also learn to identify performance bottlenecks, optimize the system, and improve overall stability. And finally, we will understand how the changes are reviewed, submitted, and contributed through the Garrett for AOSP. So we have finally reached at the last stage of our roadmap, but this isn't the end of the journey. It's where everything we have learned comes together. By this point, you will have solid understanding of Android internals from the application layer all the way down to the Linux kernel. Now it's time to turn that knowledge into real career opportunities. So Android platform interviews are very different from Android application interviews. You are not just expected to know Android APIs or write application code. Interviewer wants you to understand how Android works internally. They might ask you how Android application starts, how binder works, how the boot process flows, or how Android communicates with hardware. By the time you reach this stage, you will already know the answers because you have learned the concepts from the very basics. We will also work through real world debugging scenarios. We will learn how to analyze logs, identify the root cause of issues, and think through problems like an Android platform engineer. That's exactly the kind of thinking companies look for during the technical interviews. As you gain experience, interviews become less about individual components and more about designing complex systems. We will discuss architecture, trade-offs, and how different Android components works together to solve real engineering problem. These discussions will help you build the confidence to approach senior level Android platform interviews. So by the end of this roadmap, you won't just know what Android components are. Instead, you will understand how they work together to build a complete operating system. Whether your goal is to become an Android platform engineer, contribute to AOSP, work on custom ROMs, or simply understand Android at a much deeper level, this series is designed to help you get there. So, if you are excited about learning Android from inside out, subscribe to the channel and let's begin this journey together. So, the next, I will see you in the very first deep dive episode. Thank you.